Hey guys, welcome to video 78. Today we're going to design a transformer coupled Class A single-ended power output stage using the EL84 in the pentode mode. If you remember the last two videos, we used the EL84 wired up as a triode, and to do this we just short the screen grid directly to the plate. Now over here on the right I've got the curves for both the pentode and triode mode for the EL84 superimposed on the same plot, and we can use these to get an idea of why it might be better to use the pentode mode for our design this time. So to do this, let me just draw an arbitrary AC load line. We'll say that extends from a VPK cutoff of 300 volts to an IP sat of 50 milliamps. And let's assume that our Q point is right here in the middle at VPKQ equals 150 volts. Now, remember, we can swing in the negative direction on the plate until our operating point intersects the VGK equals 0 curve. For the triode mode, that's right over here, and it looks like about maybe 85 volts. If we're using the pentode, we can swing from 150 all the way over to this point where we're intersecting the VGK equals 0 curve, and that looks like maybe 10 volts or so. So we can get a maximum negative plate signal swing in the triode mode of about minus 65 volts, or if we're using the pentode, we can swing in the negative direction about 140 volts. Now we're assuming that both plates can swing in the positive direction all the way to 300 volts, so that's a 150 volt positive swing. But because we've got such a big difference in negative swing, here we're limited to minus 65 volts, while the pentode mode can go minus 140 volts. We're going to get a much larger unclipped maximum output power using the pentode than the triode. And another advantage of the pentode that's not obvious here is that it's going to have much higher voltage gain than the triode. Now let's go on over to the next page and take a look at the circuit we're going to be working with. And here it is. Now, designing from scratch, probably the first thing we would do is pick a power supply voltage. And for this type of amplifier, using an EL84, anything from maybe 150 volts to 300 or a little bit more would be a reasonable power supply value. In this case, I'm using 200 volts, and that's because that's the power supply I had available that'll work well with this tube. So that's why I'm using it. Now, we're also using an 8 ohm loudspeaker, very common speaker impedance, and we're also bypassing our screen grid to ground. We don't necessarily need to do this, but we're going to go with that for now, and I'll talk about what happens if we leave this cap out later. Now, there's no one right way to design an amplifier. A lot of times it might depend on the parts you have around or what you can get for a reasonable price. In this particular case, since our VPKQ is 200 volts, what I'm going to do is pick an IPQ somewhere on this line on the graph that's below our PD equals 12 watt maximum power hyperbola. Now, 50 milliamps would be a good choice, but for reasons I'll explain in a minute, I'm going to go with 40 milliamps. And I'm going to write our IPQ value over here, 40 milliamps. And now what we're going to do is construct an AC load line based on this Q point. Now, as usual, we want our Q point centered on the AC load line, and that means then, since we're running at 40 milliamps, our IP sat value is going to be 80 milliamps, and that's right here. Now let me switch to red to be consistent with my other videos, and our AC load line then extends from 80 milliamps through the Q point, and of course it goes off of the graph here, but if we were to extend the AC load line and the VPK axis, they'd intersect out here at 400 volts. And what we're going to do next then is determine our reflected load resistance based on the slope of our AC load line. R prime L is equal to, in this case, VPK cutoff divided by IP sat. So that's 400 volts divided by 80 milliamps, which equals 5 k ohms. So what we need to do next then is find a transformer that will step the 8 ohm loudspeaker impedance up to 5 k ohms and be capable of handling a DC bias current of 40 milliamps. I've already got a tab open to the Hammond single-ended output transformer page here. This is the 125 SE series transformers, and if we go down and look at what they have available, we see that the 125 BSE is capable of handling a maximum DC bias current of 45 milliamps, and that meets our requirements. So we could use that or any of these larger transformers, but probably the BSE is going to be the least expensive of all of these choices. So if we go over and look at its specifications, we see that it's capable of matching an 8 ohm speaker to 5,000 ohms on the primary, and that's exactly what we need. So we're going to use this transformer with the black and yellow leads connected to our speaker, and then on our primary we'll have a reflected load resistance of 5,000 ohms. And of course we probably want to know what this thing's going to cost. So on the next tab I've done a little bit of price shopping here, and we can see that it's going to cost anywhere from probably $53 or so on up to the $60 range, 65 or so. So we're going to spend at least $50 on this transformer unless we can find a used one or something equivalent on eBay or something. All right, so now let's go back to our schematic, and we can now write our transformer specification on here. We've got a Hammond 125 BSE, and now the next thing I want to do is take a look at my screen grid current. Remember, the general rule of thumb is that the screen grid current I sub s is going to be approximately equal to 0.25 times IPQ. Now IPQ is 40 milliamps, 1/4 of that is going to be 10 milliamps, so we're going to have about 10 milliamps screen grid current. So let me write that in here, 10 milliamps. And now we're going to determine R sub S, our screen grid resistor. As a general rule of thumb, I set my screen grid voltage to about 75% of my plate voltage. So that is VG2 is approximately 0.75 times VPK Q. In this case, that's 0.75 times 200 volts, or about 150 volts. So we're going to have about 150 volts here. That means we're going to drop 50 volts across RS. So R sub S is 50 volts. Divided by I sub s, 10 milliamps, and that's 5 k ohms. Now I'm going to use the closest standard value, which is 4.7 k ohms, and we also want to look at the power dissipation of this resistor. So P sub RS is equal to I sub s squared times RS, and that's 10 milliamps squared times, let's use the theoretical value of 5 k ohms, and that gives us a power dissipation of 0.5 watts. And just to be safe, we'll use a 1 watt resistor here. Okay, so we use 1 watt, and what we've got here then is 4.7 k at 1 watt. And we're getting a little bit tight here, so I'm going to clean things up, and give me a second to do that and we'll move on. All right, let's clear this out. And before I erase this one, I just want to mention that we also could calculate R prime L by using VPK Q divided by IPQ. but I like to use the load line just because I like graphical representations of things. Algebra is great, but I like pictures too. So anyway, we could have just used this value, but I used the load line here just to emphasize what was going on. Okay, so again, let me clear this off. And now we're going to determine the value of RK. Remember, for a pentode, the cathode current is equal to the plate current plus the screen grid current. So in this case, we've got 40 milliamps plus 10, or 50 milliamps of cathode current. Let me write that as an equation here. I sub K equals IPQ plus I sub S. All right, now if we come over here to our plate curves, note that the Q point is located right on the VGK equals negative 8 volt curve. So R sub K is equal to negative VGK divided by I sub K. And that's 8 volts divided by 50 milliamps, which equals 160 ohms. And the closest standard value is 150, and that'll work fine, so we'll go with 150 ohms. And the power dissipation here is going to be a little less than half watts, so we can go with a half watt resistor in this position as well. And I think what I'll do next is determine the parameters for our EL84. We could do this by scouring through the data sheets, which I have here, or we could get these parameters directly off of these curves. We've seen how to do that in previous videos. But in any case, no matter what we do, we're going to end up here with a GM of about 10.4 millimos and a dynamic plate resistance of about 30 k ohms. Now, mu isn't normally specified for pentodes, but if we use GM times R prime P, that gives us a mu of over 400 in this case. So we should get pretty decent voltage gain out of this circuit. But anyway, these are the two parameters we're interested in. And next, let's determine the turns ratio of our transformer. We know that NP over NS is equal to the square root of R prime L divided by RL. So we've got the square root of 5K divided by 8, and that's the square root of 625, which gives us a turns ratio of 25. All right, so we've got a turns ratio of 25 to 1 on our transformer. I'm going to write that up here so I don't forget it. 25 to 1. And let me clear out some space here. And the next thing I want to do is determine the small signal plate resistance R prime P. All right, so remember, R prime P is equal to R prime L in parallel with little r sub P. So we've got 5 k ohms in parallel with 30 k ohms, which is about 4.3 k ohms. All right, now we can determine the voltage gain of the EL84 at the plate with respect to the control grid G1, and we're going to call that again A prime V. It's equal to GM times R prime P. So we've got 10.4 millimos times 4.3 k ohms, and that gives us a voltage gain of about 45. Okay, so it's pretty good, and we expect to get pretty decent voltage gain from a pentode. Now, the actual voltage gain, AV, is equal to A prime V times NS over NP. So we've got 45 times 1 over 25, and the actual voltage gain referred to the load, our speaker, is about 1.8. And how about next, let's determine the minimum plate to cathode voltage, VPK minimum. And remember, that occurs when our Q point or operating point moves over to the left and intersects the VGK equals 0 volt curve. And in this case, it looks like that happens over here. It may be around 15 volts. So VPK minimum is 15 volts. And using this, we can determine the maximum negative voltage swing of our plate. Okay, that is V prime O minimum is equal to negative VPK Q plus VPK minimum. So that's negative 200 volts plus 15 volts, which is 185 volts negative. Okay, so our plate can swing negative 185 volts. We'll assume that VO max, or actually V prime O max, is equal to IPQ times R prime L. That is, we're moving from our Q point out to where the AC load line intersects the x-axis at 400 volts, and that's 200 volts in this case. So we have a reasonably symmetrical clipping situation here. We can move negative by 185 volts and positive by 200 volts, and that's pretty good. All right, let's clear the decks here, and we're going to determine our actual output voltage swing and our output power levels. Okay, so VO max is equal to V prime O max times NS over NP. So we've got 200 volts times 1 over 25, which gives us 8 volts. Okay, so we can expect our output voltage to swing to positive 8 volts before we hit clipping. And remember, it could also be negative 8 volts. It depends on how we have the phase of the transformer set up, where the phase dots are. But right now, it's arbitrary. Okay, and VO min is equal to V prime O min times NS over NP. So we've got negative 185 volts times 1 over 25, which is about negative 7.4 volts. So we're going to clip first on our negative going output, but they're pretty close together. All right, so now let's determine our maximum output power, and we choose the smaller of these two in magnitude, so that's 7.4, which gives us PO max equals 7.4 squared divided by 8, which is 6.8 watts peak. And remember, if we're dealing with a sine wave, PO RMS equals PO max divided by 2, so that's 3.4 watts RMS. And remember, the maximum possible output power we could get is 1/2 of PDQ. So for this circuit, PDQ is equal to IPQ times VPKQ. That's 40 milliamps times 200 volts, or 8 watts. So the most we could expect theoretically here would be 4 watts. And we're getting, where the heck is it? 3.4 watts. So that's not too bad, not too far off from the most we could get. Now, there's just a few more things we need to determine here before we're done. The grid resistor RG, if we look through the data sheet, this can be as large as 1 megohm. So I'm just going to go with 470 k ohms here, and that'll work fine. And the capacitor values, well, for C3, 1 microfarad would work okay. And remember, it has to be rated for at least 150 volts, so probably a 250 volt capacitor here. Our input coupling cap, 0.1 microfarad, is going to work fine. And for our cathode bypass cap, 100 microfarads will work well there as well. This doesn't have to be a very high voltage capacitor. We only have 8 volts dropped on our case, so a 25 volt capacitor here would work just fine. And again, we're going to talk more about how to choose these capacitor values in a later video. I don't want to get into that now. This is already long enough. And that leaves me with one more thing I want to mention before we go to the next screen and consolidate all this stuff. And that is, keep in mind that these pentode curves are specified with a screen grid voltage of 250 volts. And we're operating over here with 200 volts roughly on our plate and 150 volts on the screen grid. So these curves aren't going to quite be as accurate as we'd like. The effect of using these lower voltages over here is going to be to move these curves all down a little bit. We're going to compress them vertically somewhat. So our actual IPQ is going to be a little bit lower than this, and likewise our screen grid current is going to be lower. And this ultimately results in a little bit lower output voltage swing limits and lower output power, but we'll see that when we actually look at the results of the circuit that I prototyped. So let's go on over to the next page and see what we've got. Now, I didn't carry over all the calculations for intermediate values and all the formulas, but as usual, I boxed all the theoretical values in blue and the measured values for the prototype circuit are in red. I also extended the voltage axis of the plate curve graph so that we could see the entire AC load line here. Now, coming over to the circuit, we predicted a plate current of 40 milliamps. The actual plate current was 33.4 milliamps, and all the rest of the associated voltages and currents were reduced by an approximately, proportional amount here. Our voltage gain came out about the same as calculated value, but overall the maximum unclipped output power was about 1.9 watts RMS versus 3.4 calculated, which is a bit lower, but it's still usable as a practice amp, so it's not a bad design overall. All right, now what I want to do next is go over and look at some of the voltages that I obtained with the measured experimental circuit, and here with an input of 1 volt peak to peak, we get an output of about 1.6 volts peak to peak. Again, that's our voltage gain of 1.6, and there's not much distortion present. It's pretty clean. And if we increase V in a little bit more to 4 volts peak to peak, we get 6.6 volts peak to peak out, and we're starting to see some distortion here. These upper peaks are a little bit narrower looking than the bottom peaks, which are kind of spread out, stretched out a bit. So we're getting some distortion, but it's not too bad. And if we really overdrive it, this is what we get. If we put in 10 volts peak to peak, we get out about 11.7 volts peak to peak, but it's pretty distorted. We're getting a lot of clipping on the top, reaching a max value of 6.1 volts, and down on the bottom we're maxing out at about minus 5.6 volts peak. Now if we do a FFT spectrum analysis on this, here's what we see. Our fundamental is about 4.5 volts RMS, and our second harmonic is down to about 0.4 volts RMS. Third harmonic pops up a little bit higher. The fourth is 0.22 volts, fifth 0.056, and our sixth harmonic drops way down to about 1 millivolt RMS. Now, we can get an estimate of the total harmonic distortion for this amplifier by using this formula over here, where THD, total harmonic distortion, is the square root of the second harmonic voltage squared plus the third squared, fourth, and so on. And we could add all of these up, but if I stop here at the, let's see, this would be 2, 3, 4, the fifth harmonic, it's going to give us a reasonably good estimate of the total harmonic distortion, which comes out to be about 14.3% at this drive level. Now, if you want to have some fun with this, something you might want to try is to take a screen capture of just this spectrum display here and give it to ChatGPT and ask it to determine the approximate total harmonic distortion and see what it comes up with. It should come up with about 14.3%, but you never know. Sometimes it hallucinates, and it could be kind of an interesting thing to look at. Now, I thought it might be interesting to look at the plate voltage with an applied signal. So if we come over here, this is the EL84's plate voltage with a 9-volt peak-to-peak input signal, and we can see we're reaching a Vmax on the output at the plate of 149 volts, and we're starting to clip here on the negative going swing at about minus 167 volts or so. So we do get the really big voltage swing on the plate that we would expect. I also wanted to show you what happens if we pull out the screen bypass capacitor as well. So I took a few screen captures with the cap removed, and with 4 volts peak to peak applied, this is the output voltage we get here in the yellow, and you can see it is a pretty good undistorted version of the signal, and it really doesn't seem to make that much difference if we use that capacitor or not. The voltage gain is a little bit lower without the cap, but not significantly. And if we overdrive the amplifier, or at least start to by applying 10 volts peak to peak on our input, we can see the output is about 10 volts peak to peak as well. I'm just using a different scale here, and the distortion is not too significant yet, but overall I would say using the bypass cap on the screen really doesn't change things that much. So you can either use it or not, and see what happens. You know, you might like it a little better one way than the other. All right, and finally I'm going to leave you guys with a picture of the experimental circuit here. Right, this is my EL84, and rather than using a loudspeaker, I used a 5-watt ceramic resistor here, and this thing did get pretty hot when I was doing the testing, so we're getting some fair amount of power out of this thing. And I didn't have a 125 BSE, so I used a 125 DSE, but basically it's going to give you the same results. And that's it for today's video. We'll continue along these lines with some more pentode stuff in the next one, and I'll see you guys then.